Good morning, grade 10s, and welcome to the very first lesson on analytical geometry, the distance formula. For now, I don't want you to write anything. I just want you to focus on what's in front of you, and that is the line AB. A has an x-coordinate of 1 and a y-coordinate of 2, while B has an x-coordinate of 6 and a y-coordinate of 4. Now, I'm sure you've noticed that the heading says the distance formula. So what we are going to consider is how one would calculate the distance between the points A, B. In other words, the distance of the line segment AB. Let's think about this. If we have the Cartesian plane and the coordinates of 2 points, we can link up the coordinates to the x and y axis. First things first, let's make a right-angled triangle. So this dotted line over here is parallel to the x-axis, while that dotted line is parallel to the y-axis, making a right-angled triangle. Any 2 points on the Cartesian plane can be connected by a diagonal line, and then that line can form the hypotenuse of a right-angled triangle. We could have made the right-angled triangle over here above the line AB, and we would be working with the exact same concept. All right, basically you connect the 2 points together by means of a right-angled triangle. Now let's have a look at this coordinate A. If we were to drop down to the x-axis, we know that the x value, the x portion of the coordinate of A is a number 1, while if you were to drop this B coordinate down to the x-axis, you know that we would be sitting at which number here? Number 6, right? So there we have a 1 and 6 respectively. So if I asked you, what is the distance between this part of the x-axis to this part of the x-axis? In other words, from 1 to 6, how many little bunny hops would you have to make? You guessed it. It's 5. What did your brain actually do to calculate those 5 units? It took the big value on the right-hand side and it subtracted the value on the left-hand side. Now, I hope this is reminding you of functions where we said the distance of a horizontal line is the x value on the right minus the x value on the left. So that's where we get the 6 minus 1 equals 5. Now let's repeat the same for the y values. So let's work out this vertical distance here. So this little part of the right angle triangle. If we take coordinate B, because we know that the y part of the coordinate is a number 4, it links up to 4 on the y-axis. Likewise with coordinate A, because the y part of the coordinate is a 2, it links up to 2 on the y-axis. So this segment of the y-axis from 2 to 4 is exactly the same distance as this part of the triangle. So how do we calculate this vertical distance? Remember from functions, we say a vertical distance is the top y value subtract the bottom y value, and we get 4 minus 2 equals 2 units. So now we have 2 out of the 3 sides of a right-angled triangle. So what word is coming to mind? How do we find the hypotenuse of a right-angled triangle if we have the 2 given sides that meet at 90 degrees? Of course, we use Pythagoras. So this distance AB is going to be the sum of the squares of the other 2 sides. So here the 2 units squared plus 5 units squared will give you AB squared. Once we do the maths, we see that AB squared gives us 29. So if we want AB's distance all by itself, we're going to have to get rid of the square. How do we undo an exponent? We square root. So the distance AB is the square root of 29. Yes, if you put this in your calculator, you can convert this to a decimal, but the format that it's in right now is called simplest surd form, and it's actually a very nifty, convenient format of a number, because this right here, it's not a perfect square. So if you convert this to a decimal, there will undoubtedly be, it will be a non-recurring, non-terminating, irrational number, and so you would have to round off. So if you can, keep it in simplest surd form so that you can, if you ever have to work with this distance, you have the full value right there as the square root of 29. I know it looks strange, but you will get used to it. Okay, so now let's apply this exact concept, but without specific numbers, so that we can perhaps generate the distance formula. So I've duplicated that image, but instead of giving actual values as coordinates, I'm labeling this part of the A as the X value of A and the Y value of A. So that's where we use these little subscripts where your X is still in lowercase but small. You make a baby capital A right next to it. Likewise, this is the X value of B and the Y value of B. Let's go ahead and make that right angle triangle again and think, how do we find a horizontal distance? Well, now instead of having numbers, I can say that represents the X value at A, and this point over here is the X value at B. A horizontal distance is the value on the right minus the value on the left of the X axis. So this is xb minus xa. The X value of B minus the X value of A would give you this horizontal distance. Likewise, if we took the Y value at B and we subtracted the Y value at A, we would get that vertical distance right there. Now I know these are binomials, in other words, two terms, so let's pop them in brackets when we apply Pythagoras. So this distance AB would be the horizontal distance squared, so xb minus xa squared, plus yb minus ya, the vertical distance squared. The hypotenuse is the sum of the squares of the other two sides, all right? That will give you the hypotenuse squared. And so if we now keep all these variables right there, it's okay that we're not dealing with numbers. These can represent any coordinates A and B. If we were to get AB all by itself, we would get the square root of all of this on the right-hand side. I know it's scary looking, it's a massive formula, it's probably the biggest one you've had to memorize thus far, but that right there is the distance formula. So, like I just said, the distance between any 2 points A and B can be given by this distance formula. It's very important that you memorize this formula because we're not going to necessarily give it to you in an exam. And so just remember that the plus is outside of the brackets in the middle and there are minus signs in the brackets. And this order, see how it says AB is equal to the square root of the x coordinates of B minus the x coordinates of A. You don't actually have to worry about the order of the x coordinates of B and the x coordinates of A. You could swap these around because at the end of the day, we are squaring that answer. So a negative 3 squared will be exactly the same as a positive 3 squared. So the order inside the bracket is not essential, but the fact you must keep your x's together. So it's the difference between your x values squared plus the difference between your y values squared. Don't go and put the same coordinate, an x and a y, in brackets. It's the x's in brackets together and it's the y's in brackets together. Right, so you don't always get A and B. These letters can interchange, and we'll deal with that in example 2. But for now, example 1, you are required to find the distance between the points 1 and 5 and negative 2 and 3. Now see how these points have no labels. They're not called A and B. They could be called X and Y. Oh no, not X and Y. That would be super confusing because of all the X's and Y's already. So we would never call a coordinate X or a coordinate Y. We would maybe call it R and T, V and W, etc. So if you are not given labels, you can make it easier for yourself. You go and pop an A in front of the one coordinate and a B in front of the other coordinate, and if you like, go and label the 1 of the coordinate A as the X value at A. The 5 of coordinate A will be the Y value at A. Link them up so that you can see exactly what you need to substitute into the relevant spaces of this formula. So here you can see AB, I'm applying this formula straight away, is equal to the square root of the X value at B. Let's go and look at the X value at B. It was -2, and so I substituted -2 into the formula, minus the X value at A. What was the X value at A? It was a 1, so I substituted 1 into the formula. Close bracket, square, plus, open bracket. The formula now says we need the Y value at B, so I go and take the Y value at B and I substitute it into the formula to get a 3 over there. And then we subtract the Y value at A. The Y value at A was a 5. Pop it into the formula, and now's the easy peasy part. Once you've substituted the values in correctly, your job is done. You don't have to show much more working out. You are allowed to whip out your calculator and get the final answer. You can keep it in simplest surd form unless we ask you to round off to a certain number of decimal places. It's as easy as that. Okay, so this example requires us to work with the distance formula and apply it to a triangle that's on the Cartesian plane. Now, this triangle is not given to us, but its coordinates are. So sometimes it is helpful to sketch the triangle on the Cartesian plane in order to be able to visualize it a bit better. Anyway, for now, I want you to realize that the distance formula can be applied to more than one coordinates, not at a time, but separately. So if we were to have to work out the perimeter of this triangle, you could just pair up the coordinates with each other without requiring a sketch. So we know that if this is the triangle ABC, one side would be AB. So you could work out the distance of the line AB using that formula right there. Then the other side of the triangle would be A connected to C. So now instead of a B in my formula, I have the X value and the Y value of coordinate C. And that way I can find the distance of the line AC. And last but not least, you can even connect B and C together. So we could find the distance of the line segment joining the coordinate B and C by using the difference between the X values and the difference between the Y values of the coords B and C. Right, I'm going to sketch it in any case just so that we can see. The coordinates A would be more or less there, 1 and -3, B 7 along the x-axis, 3 up, and C 4 across and 6 up. So if we connect the dots, our triangle would look something like that. Now let's go and apply this formula so that we can get the lengths of each of the sides of the triangle and then use those lengths to calculate the perimeter by adding them all together. So if we go and substitute in the correct values, you'll see that I have merely taken my X values of coordinate A and my X and my Y value of coordinate A and my X and my Y value of coordinate B and substituted it into the relevant spaces. The X value of A is given by 1, and so I pop in a 1. Y value of B was a 3, pop in a 3. Y value of A was a -3, pop in the -3. Do you see how the negatives together will become a positive? So this is going to become 3 plus 3, which is 6 squared. Righty. If you like, just be very, very careful with your substitution and plug it straight into your calculator and it will give you 6√2 as an answer. Now, unless we ask you to round off your answer to a certain number of decimal places, you are welcome to leave it in this format, which is simplest surd form. Right, then we can deal the line AC, substitute in the relevant values. Do this slowly. It is going to take you some time to adjust to this relatively complicated formula. So be thorough and practice this a lot. Today's homework makes you do this over and over and over again. So hopefully by the end of today, you will be confident. So there we get 3 root 10 is the distance of AC. And then BC, substituting in the difference between the x parts of the coordinates squared added to the difference between the y's. So let's see, we've got a 6 and a 3 as your y, a 4 and a 7 as your x's, and you should get 3 root 2 units as that distance. Now, to find the perimeter, we're going to add them together. Apologies if my voice was cut off. For perimeter, we're just going to add the 3 distances together. So we have 3 root 10 plus 6 root 2 plus 3 root 2 gives us 22,21 units. So that's the perimeter rounded off to 2 decimal places. Now we want to know, is this triangle a scalene triangle? Well, we don't have a repetition of any values, so all 3 sides of this triangle differ. So yes, this triangle is a scalene triangle. If there were 2 sides that were the same length, then the triangle would be isosceles. And if all 3 sides were the same length, then the triangle would be equilateral. I hope you remember that terminology. Now we have to prove whether or not the triangle is right-angled. Now I hope you can remember that in a right-angled triangle, the theorem of Pythagoras would work. In other words, if we were to square the hypotenuse, it would be equal to the sum of the squares of the other 2 sides. Play that again if you need to. That's the theorem of Pythagoras. So what we need to do is check to see if the theorem of Pythagoras works. Check to see if it holds, if it is true. So I'm writing down the theorem of Pythagoras, and now I'm going to break it down into 2 halves. The left-hand side of the equal sign, which is AC squared. So that's 3 root 10 squared, and if you pop that into your calculator, you're going to get 90 as a result, or you could do it in your head. 3 squared is 9. The root of 10 squared would be 10. 9 times 10 would give you 90. Let's double check the right-hand side of the theorem of Pythagoras. If you take 3 root 2 squared and add it to 6 root 2 squared, well, 3 squared is 9, root 2 squared is 2, so 9 times 2 will give us 18, plus 6 squared is 36, 2 squared, root 2 squared is just going to give you 2, so 36 times 2 is going to give us 72, 72 and 18 together gives us 90. So look at how we've dealt with the left-hand side of Pythag separately from the right-hand side of Pythag, and now we can conclude that the left-hand side of the theorem is equal to the right-hand side of the theorem, so the theorem holds. Pythagoras works for this triangle, so we can conclude that ABC is indeed a right-angle triangle. And that is that. Have a look at your homework, and please reach out if there's any queries.